Hello, welcome back. This is Calculus by Dr. Oz. Today we are going to go over an exercise where we're going to find equations of tangent lines. And finding equations of tangent lines is one of the main themes of Calculus 1. And to be able to come up with the equations of tangent lines, you should have the slope of the curve at the given point. You should have that piece of information, and since the point is provided to us, we're going to use the point slope form of the equations of tangent lines for both cases. Okay, in fact, we're given 3 points for each parametrized curve, and we will have 3 different tangent lines popping for each case. And I don't want to give you any hints, but just to show you what you're going to be getting into, first of all, we will be able to graph the parametric equations and get good visual, and then check what t values correspond to given points in the statement of the question. And once we determine the t values, then we're going to calculate dy over dx in terms of the parameter, and we will have 3 different locations, as you see, and in each of them you have a different tangent line. And in the second part of the question, the curve corresponds to an ellipse, and in the same way, we're going to determine what t values correspond to the given points on the ellipse, where we're going to write down the equation of tangent lines. And in this case as well, we're going to write dy over dx, which is telling us the slope of which hides the information of the slopes on the curve. We're going to sort of like write that in terms of the parameter t, okay? All right, so I'm going to split this video into 2 parts, and let's get started. All right, let's start with part A, and let me just tell you one thing. This is one of the staple tasks of Calculus 1, which is finding equations of tangent lines for given curves, and to achieve that goal, we need the first derivative of the function. But unfortunately, these equations are parametrized, so we have the parametric equations, not the rectangular equations. So what we can do here is to use the formula dy over dx written in terms of dy over dt and dx over dt by dividing top and the bottom by dt, okay? So that we can talk about the derivatives, because dy over dx doesn't make any sense for parametric equations because there's no x here. Like y is not written in terms of x, but y and x are both functions of time, so or t, parameter t. So it doesn't make any sense to work with dy over dx, but with this little trick here, we'll look at dy over dt, which is 3t squared plus 1, divided by dx over dt, which is 4t cubed. Another way to handle this problem, as a side note, is that, you know, you can go back to the rectangular equation form, so that you have the y equals f of x form, and then you can just take the derivative in the classical sense, and find the slope, and it slopes, in fact, at 3 different points, and you can write the equation of the tangent line for each case. But I think since we are given the parametric equations, this is the most convenient way to start with, since we have this formula here. Okay, so what I'm going to do now is, like, I'm going to have 3 different slopes, okay, because I have 3 different tangent lines to start with at different points. So this is at 2, 0, 3 and negative 2, and 18 and 10. Okay. So in one case, I'm going to plug in 2 and 0. We have to know also what t corresponds to those points, right? So for t, for the point 2 and 0, I think t is supposed to be 0, okay? Because as t equals 0 and x equals 2 and y equals just 0, that's how you get the very first point. And for the second one, for the second point, let's see what t could be. I want x to be 3 and y to be negative 2. to make x 3, t has to be either -1 or 1. Okay, but in the meantime, I want y to be -2, so I think t equals -1 is a better choice. In fact, you get x equals 3 and y equals -2. And in the last case, we have, let's see, t equals, I want x to be 18, y to be 10. So to make x 18, I think t is supposed to be 2 or -2. But in the meantime, I want y to be 10, right? So then 2 cubed plus 2, that takes you to 10. So t is supposed to be 2. Okay? So this way I can go ahead and find m1. m1 is going to be dy over dx evaluated at t equals 0, and you get 1 over 0, which is undefined. So the very first slope is undefined, so I should expect a vertical tangent line. And the second one is for t equals -1. So 3 -1 squared plus 1, 4 -1 cubed. So that is 4 divided by -4, so it's -1. Okay. All right, that's good. And the last one is t equals 2. Let's do this in one shot. 3 times 2 squared. 2 squared is 4. 4 times 3 equals 12. And the top is 13, and the bottom is 2 cubed times 4, which is 8 times 4. So that's 32. I want to leave those numbers exact. Try not to use the decimal, like numbers with decimal places at this moment, because we want to keep the exactness of the slopes at this moment. And then, since we have all the slopes and the points, so we can go ahead and write down tangent line 1, tangent line 2, tangent line 3. Okay, so here we go. We have the point slope forms of equations. So I'm going to write y minus the y coordinates equals m1 times x minus the x coordinate. But since m1 is undefined, I don't have the regular point slope form. In fact, I do have the vertical tangent line, right? And the vertical tangent line should be the very x coordinate of that point. So here we go. X equals 2 is the equation of the vertical tangent line. All right, so for the second part, we have the point 3 and -2. Y minus the y coordinate of the point equals m2, which is -1, times x minus the x entry of the point. So that is this. You can simplify this further if you want to. And lastly, you have 18 and 10. So y minus 10 equals m3 times x minus 18. Okay? And go ahead and simplify those quantities. So in this way, by calculating dy over dx, by using dy over dt and dx over dt, we were able to get 3 different slopes at 3 different points, and for that reason, we got 3 different tangent lines. All right, we're done. But I want to show you the graphs here, because we have 3 different tangent lines to the curve at different locations, and I want you maybe to pause the video at this moment and graph the parametric equations together with the tangent lines. Okay, so we have 3 different tangent lines, and here we go. That's what we got. Just to give you some visuals out of that. So we have one point corresponding to t equals 0, which is right here. Okay, and then another one equals another one is for t equals 2, and also t equals -1. And at t equals -1, we had a vertical tangent line, and that's the proof of that. We have, in fact, the vertical tangent line at this point here. And at t equals 2 and at t equals 0, we have those points here, and you have obviously positive and negative slopes, and that's exactly what we got in our analysis here. All right. So this is already a long video. I'm gonna end this here, and please move on to my next video to see what I'm going to do for part E. Bye.